Farook and Professor Pradeep for inviting me for this program, and thanks to Dr. Jerry and Reggie Thomas for a nice introduction. And the title of my presentation is Light-Induced Self-Assembly in Precision Noble Metal Nanoclusters. Noble Metal Nanoclusters, new directions and applications, and coming from University of Calicut, and this university is very close to this institute, nearly 10 kilometers from this place. And basically, we are working on small particles like what Professor Pradeep showed yesterday. So these materials are very small, having a size is less than 1 nanometer, having an optical properties which is entirely different from the plasmodic nanoparticles. So what usually these nano clusters, people started using like as a assembled materials or a static materials or building blocks to assemble and form superstructures. That is what I showed here. So using this kind of building blocks, we can make beautiful structures. So when you look at this picture here, you can see that like in case of like for chemists, we need some kind of chemistry to connect these individual nanoclusters into big entities, or making the assembly we need a reason or we need a chemistry behind this one. So people are using different interactions, nanoscale interactions such as anti-steric interaction, van der Waals, CH5 pi, electrostatic, hydrogen bonding, and so on. And so I'm showing some of these examples here, and this is a paper from Nanoclusters group. Here you can see that there is a COH group, or they used a silver AG44 nanoclusters connected with mercato benzoic acid. But so what is happening? There is a COH group. It can undergo that COH of one cluster and COH of another cluster. They can attract each other by hydrogen bonding. So this small, even though it's a small interaction or attractions, they can hold nanoclusters into a superstructure. So if you have patience, you can wait and you can see how this nanocluster is assembling. And this assembly will be different. Like that is what I have shown here. And based on our interest, we can make different structures. Likewise, we chemists usually doing this essentially and making these fascinating superstructures. So based on our interest or our vision, we can make this small, beautiful or big structures. So this is one of the examples using hydrogen bonding, and this is another example. Here they have used an alkyl chain. So when they heated this alkyl chain, can attract each other by means of a van der Waals attraction. So they can hold the nanoclusters and assemble and loop and form the big nanostructures, beautiful structures like nanowires. And this is another. Here the gold. If you are making like a gold like a D10 configuration for a gold, so the D10 can attract each other. That is called metallophilic interactions. But like now the question is, I can make it. So my question is it possible to get back my cluster into individual nanoclusters? That is, we are starting from a cluster and assembling a superstructure, but in the superstructures, the atomic properties or the optical properties of nanoclusters are intact. We are not changing. Okay, so now my question is it possible to get back the superstructures into individual nanoclusters? So that means there should be a reversible assembly, or there will be dissociation without changing the optical properties of nanoclusters. So here we can see that we can make this one and we can disassemble and we can remake it. That is what we enjoy in our childhood, and that is what my son is doing right now. But my question is it possible to make this assembly? We are happy, we know that we can make this assembly, but are you sure that is it possible to make the reassembly? But whatever examples I showed there in the first 3 slides, we cannot reassemble or cannot disassemble into individual nanoclusters. Once you make this assembly, there is an assembly. Okay? It's a stable assembly. We cannot get back into individual nanoclusters. Okay? We are always curious, so we thought that how to make this assembly. So in my group, we are working to assemble or creating this architecture like superstructures or beautiful superstructures by means of light. So why we are selected, because if you are selecting a chromophore, light absorbing chromophores, like based on the photophysical properties of these molecules, we can switch this molecule. We know that this molecules we can switch it. For example, if you take an azobenzene in presence of a particular wavelength of light, it will be in the trans geometry. When you switch, when you shine this molecule with another wavelength of light, appropriate wavelength, then it can back to cis geometry. So when you go for this cis and trans geometry, we can create a dipole. For example, in case of azobenzene, if there is a cis geometry, there is an induced dipole. And so if you have a nanocluster with the azobenzene in the cis geometry, then there is a dipole, and the same dipole is creating nearby nanoclusters. This dipoles can attract each other, and so that means these nanoclusters can induce the assembly and form a superstructure. That was our aim. And the second case I am discussing here, we used a coumarin molecules. Coumarin is having a double bond. It can undergo 2+2 cyclodissociation. That is what your MSc classes teachers taught you. So that means when you go a 2+2 cyclodissociation, this nanocluster and other nanocluster coumarins can undergo 2+2. That means they are holding nanoclusters together and form the superstructure. Then these were the two molecules we selected. That is in two different time scales we have selected this molecule. So then we will be discussing what the So for first case, we synthesized azobenzene thione molecules, synthesized nanoclusters. So in a particular, basically it will be in the trans geometry, but when you shine 365 nanometer, this molecules switch to cis geometry, but when you shine with 435 nanometer visible light, it will again go back to trans geometry. That means that molecule, basically this molecule is doing like a dancing. So that means our nanoclusters have started dancing in presence of light. So when you push a light or like shining a light, this nanoclusters start to shine or nanoclusters start to dance. And then we were investigating how or what is the reality of a nanocluster in presence of light, or what is happening with nanomaterials in presence of light. And for this, what we have done, and before here also, when you take a UV spectrum, you can see that this in presence of UV light, this molecule's optical properties are changing. That is, the chromophore optical properties are changing. That is, chromophore which is functionalized on the surface of nanoclusters are photo-switching. Then, but we have to ensure that this photo-switching controls or influences the structure of the nanoclusters or assembly of nanoclusters, and we are visible in the, it is also clear in the NMR spectroscopy. Here you can see that we can see the trans geometry and the mixture of transit, and if you shine for a long time, we can see all the molecules will be in the cis geometry, and plus also we can see same thing. This is a trans AU25 nanoclusters, and this is a cis AU25 nanoclusters, and if you take the NMR spectrum in between the time scale, we can see both the mixture of cis AU25 and trans AU25 nanoclusters. When you take the details of these nanoclusters by using a microscope, TEM, so here you can see that these are individual nanoclusters. When you shine with 345 nanometer light, they start to assemble because of this dipole-dipole attraction. So in few, here 120 minutes, you can see here this kind of assembly. So when you illuminate for a long time, we can see that this is increasing, so that means forming, or the huge structures are forming. But more interestingly, when you shine with the visible light, they disassemble. Why? Because when you shine this cis made assembly, when you shine light, what will happen? Cis will be in the trans. So that means dipole will be almost zero. So that means they repel each other. So that means individual nanoclusters will be forming. So this we can repeat many times and do this experiment. So this is the mechanism basically what is happening. AU25 nanoclusters, when you shine, it will go cis AU25. So cis can attract each other and form assembly. And when you shine for a long time, this will be forming like a thick assembly. So, but we have to ensure that this azobenzene is having role. We are assuming that azobenzene in presence of light is doing all this business. So to make to ensure that this molecule is having a control, so another nanocluster, AU25 nanoclusters with a phenylenedione thiol, and when you shine light, we can see that there is no assembly. These nanoclusters are individual, and then, so that means azobenzene is making a role. Here, in the clearness, we can see that this assembly structure is increasing. In presence of UV light, this superstructure size is increasing, but when you do a visible light illumination, you can see that this is again decreasing, and this is a large area assembly. You can see while assembling, all these structures are almost uniform in assembly, but when you disassemble, we can see that these nanoclusters are disassembling and form small structures and finally form individual nanoclusters. And this is an experiment done by Professor Nanaka, and here you can see the result, basically tomography. You can see that these structures are disk-like superstructures, and this each dot represent individual nanoclusters. And then here we can see that initially assemblies are forming, individual disk-like assemblies are forming. When you illuminate for a long time, this individual assemblies superstructures then can club together and form dimers, trimers, and so on. So now, in this, the first work what we have shown that when you do a assembly with chromophore azobenzene very close to the nanocluster, what is happening? So we thought that we were interested what will happen if you keep the chromophore away from the nanocluster surface. And for this we have synthesized azobenzene with the C3 chromophore spacer length and the C9 chromophore spacer length. And we do all the difference in case of a ligand C3 azobenzene and C9 azobenzene, you see the time scale. Irrespective of the chromophore spacer length, the C3 and C9 doing the cis trans and trans to cis photo switching in the same time scale. But when you do this nanoclusters, when you synthesize this nanocluster and do the same absorption spectrum, we can see that C9 nanoclusters are photo switching very quickly, and which is very very fast compared to the C3 nanocluster. So that means when a chromophore is very close to the nanocluster, or when the chromophore is away from the nanocluster, there is a role, or based on the where the chromophore is situated on the surface of the nanocluster is having a role. So what we see here, this is a C3 nanocluster. So this assembly is this is taken in the same time scale. You see here the assembly is not complete, still the assembly is happening, or the aggregation or the arrangement is happening, but here it is almost the assembly is full. So this is because there is a steric hindrance once the C3 chromophore is very close to the nanocluster surface. So that means we see that if you do an application, or we are making a device based on this supramolecular assembly of this light-induced materials, we have to be careful that we should keep the chromophore in a proper distance, so that this assembly we can make very quickly and go for a device fabrication. So here this assembly is very slow. Because of this one, we were able to see this individual nanoclusters on the surface of this one. This is a high resolution AFM, and here this zigzag pattern shows the assembly of nanoclusters. The newly organized nanoclusters on the surface of this growing assembly. And then there's also tomography. Here you see that this assembly is not complete, but here in this case this assembly is almost complete. And then, but when you illuminate this nanocluster assembly or the solution for a long time, we can say what we see here, this individual assemblies are forming, they assemble, and then they start to grow like a chain-like assemblies. They are fusing and form a chain-like assembly. So here also, when you look at this individual spheres from here, you can see that the nanoclusters are well organized and forming a periodic assemblies. And then now the question is, here this in azobenzene case, basically there is a dipole-dipole interaction. There is no covalent interaction. It's only a dipole-based assembly. So we thought about making a molecule, a chromophore, which can undergo F2+2, so that means it can covalently connect. Nanoclusters can be covalently connected. So for this we have used coumarine molecules, and we made a coumarine thiols. And when you make a U25 nanoclusters, you can see the absorption features is 672 nanometer. And interestingly, what we see, when you illuminate these nanoclusters, you can see the absorbance is changing. That is because 2+2 is happening. And then when you do this TM, we can see that these are individual U25 nanoclusters. When you shine light, you see that these individual nanoclusters assemble and form a toroidal superstructures. And here in this STM image, you can see that this individual white dot represents individual nanoclusters. And then from the FESEM and the AFM, we see that the same morphology we can see. And when you do NMR spectroscopy, we can see that here when you do a 2+2 cyclodissociation, the cyclobutane rings are forming. So these NMR peaks represent the cyclobutane proton. So this clearly shows that here 2+2 is happening, and that is the reason why the assembly is originating, or this is the origin of assembly this toroids, when you illuminate again for a long time, we see that this toroid fuses and form this honeycomb superstructures. And we also studied in some how assembly is happening. So from here we see that individual spherical assemblies are forming, they fuse and form toroids. And we also studied the stability of toroids for a long time. That was the question from the viewers. So what we see, like when you do this assembly or when you do this microscopy, even after 1 year also the same like the toroids are existing in the grid. So this represents that or shows that this toroids are very stable. And then now what we have done, basically we have a coumarin molecules and having a double bond, and that double bond is undergoing a 2+2 with another double bond of coumarin. So we thought that like what will happen if you add a drug molecules having this kind of similar kind of double bond. So for this we used 5-fluorouracil is a drug molecules. When you do this like 2+2 in presence of drug molecules, there are 3 combinations, that is coumarin can undergo 2+2, drug can undergo 2+2, and coumarin drug can undergo 2+2 cycloadhesive reaction. So here we see that this since these these competitions are there, we are not ending with this kind of toroidal assembly. Here only we are ending with the spherical assembly. This is the beginning stage of the assembly what we have seen in the case of coumarin alone assembly, and in presence of the fluorine in the elemental spectrum as well as in the EFCS, we confirm that these drug molecules are attached on the surface of these nanoclusters, and also these are clear that there are like 2 types of cyclobutane rings. One is coming from coumarin, and one is coming from coumarin and drugs. And all this information clearly says that we can able to connect a drug molecules on the surface of nanoclusters. But in presence of light, what is happening? Nanoclusters are assembling and forming superstructures, and these clusters are, at the same time clusters are loading. So now the question was like, is it possible to disassemble in presence of light? So what we have done, when you illuminate this nanoclusters with 244 nanometer light, so what we see that these nanoclusters disassemble and form these individual nanoclusters. So that means at the same time we are molecules also here. So we successfully demonstrated that we can load drug molecules with the assembly and unload drug molecules with disassembly. So we have published this paper in small, and we dedicate this paper to Professor Pradeep on the occasion of his 60th birthday, and we are celebrating 60th birthday in this year. And then if you look at the currency of our Indian rupees, 50 rupees Indian rupees, under the UV lamp you can see there are a lot of fluorescents, and this is basically, this is our like a kind of secret codes to avoid the duplications. Especially we are very close to the place called Kundangulam, and this is the place where all the currencies are duplicating, and they have a machine, they can print it and they can sell or then distribute to all over the India, and this is happening actually. Okay, so that is the reason why Reserve Bank of India is making this kind of fluorescent tax. But when you see, these fluorescent tax are made up of like a chromophores, which is readily available in market. So any person who is not educated can nicely buy this. They are very clever. Okay, so they can buy this molecules, they can print it, and they can do all this business. So actually this work I should thank Pradeep, because when I was doing PhD with him, this idea was given by sir. So we did a lot of things, but unfortunately there was no printing devices at that time, so we were not successful. So we thought that why don't you make our own secret codes on the currency. That means in the visible light we cannot see, it's a normal currency, but when you light under, or when you shine the currency under UV lamp, you can start to see this kind of whatever information here encoded. And if you are able to record or read that information electronically by using a simple device or mobile phone, then it is very easy for us to ensure that this currency is not duplicated, but we have to ensure that this is in such a way that it should be readable all the time. Okay, so stability is an important factor, and then we should ensure that, especially in India, we like use the currency, we will fold it, we can put it in the pocket, and we do all the stupid things on the currency, and we will put it in the dress, and we will go to washing machine, and then we will dry it, wet it, all the process we will do. So we have to ensure that we should make the QR code like information which should be stable even in water, high temperature, low temperature, folding, mechanical, everything we have to be satisfied. For that reason, we have selected an AU nanoclusters. Why selected? Because it's a solid state emitting materials, and then what we see when you for making like a print, we have to make an ink. Is it basically we should need an ink? So for this, we made a nanocluster. It's already on nanocluster, but in solid state emitting and very stable nanocluster. So we made an ink in a polyurethane solution, a thick solution, and we started printing using strictly all information or thin films, everything, and we tested that all the optical properties and physical properties of this nanoclusters are stable even after printing or even in the ink also. So what finally, and we tested its thermal stability, photo stability, wettability, structurability, all these procedures, because we are using the currency for all these. We are going through our currency, all this procedure. So we tested and we found this is very stable, we can dip it, and finally we printed a QR code encrypted with the Reserve Bank of India with the permission of CSAR, and then we printed a QR code, and then we see you can read this QR code under a UV lamp. Then this process, you see this is procedure is very fast. We can read very quickly, and then you see this is a QR code currency. A QR code printed currency dipping in a water bath, and through water bath also you can read it. That is the beauty of this experiment. And so then we also use this nanoclusters for light emitting devices, and this is one of the recent works we have not yet published. And here you see this is making like we can get like a LED with the efficiency is more than 50%, and right now like gold thionet nanoclusters report the values 4%. So we are working on this work. And very recently we used this AU25 nanoclusters for high resolution, and this just accepted in small. And so summary of my work is that we are working to develop superstructures or different architectures using light, and using light we need some kind of non-chromophones. We are selecting or choosing the right chromophones so that we can make the beautiful nanoclusters, and we can do assembly superstructures, and this assembly we can use for different applications. This is what we do. And then we made like a QR code, or like we can use anti-counterfeiting applications, we can make devices and so on. And then I thank what must be I'm standing here because of Shah and Professor Vasudevan Viju. I did my EFCS with him, and Professor Brahim Yunus, University of I did my MBA with Professor Brahim Yunus, and I should thank Professor Vijay and the people who gave me re-entry to India to do science, and Professor M.K. Jayaraj, our Honorable Vice Chancellor, Dr. M. EFCS, she is my colleague, Rajavalli to my UC Bangalore, Viju Mohan from CSA Secretary, and I thank my students because of doing all experiments. Of course, I will be always with them, and they are in like a trap, in a like a particle in a box. Always I'll be following them, and so this all the experiments. I recently got this here, and she got this like small for the steroids, and used the postdoc with me, and I should thank DST for giving DST post for university for an amount of 10.78 crore. So I'm coming from though it is a very big state university or biggest state university in Kerala. Academics is very good, but research-wise it is not very good. So we are trying to push or do something from that, and DST generously gave this amount. So we are going to buy an NMR and high resolution mass spec. I hope that next year we can do lot of, or we get lot of mass spec data. We will improve our experiments, and this is a videograph. I always especially go to colleges, and here our Sar, he graduated from this college, great college, and thanks to Farook for giving all the generous help. So Professor Pradeep, when he was doing his masters here, and So work hard, dream high, and never end up. That is what I learned from my sir. Like he used to come at lab at 6:30 in the morning when I was doing I was doing my PhD. I heard that from my seniors that he used to come before that time when they were doing their PhD, and he used to leave his lab by like 7 o'clock, but he will come back again after the swimming, and then there will be always a phone call even at like 12 in the midnight, or I used to call and ask us to come to his his apartment with a laptop showing data, and we cannot escape from anytime. That was another particle in a box. So I am following the same particle in box in my lab, but that is actually that is how science will grow. And so this is about my talk. I thank all of them. Thank you.
I have a question. Sure. Really doing that talk. I have a question on the toroids, right? So first of all, do we form only with clusters, or can you use, which cluster do you use? Can you change the cluster?
Still it is a difficulty because making, like with this chromophores, making a specific nanocluster itself is a task for us. So we made AU25 and demonstrated. So we can extend this to different nanoclusters.
Which one?
AU25. And this coumarin 18.
Okay. But if you use just small nanoparticles, not precise cluster, will they still form toroids?
We are not sure, sir. We are concentrating on nanoclusters, so we focus because we have limited resources, limited manpower, and so.
And the second question is, why do the toroids form?
That is still unknown. Basically, there are some papers like polymers when you eliminate like absorbing polymers, they assemble, they can form. They are not basically toroids; they are like donut shapes are forming. So, but that rim thickness is reducing. Maybe that is one place because we are initiating with the nanocluster, small space particles.
Okay, thank you.
So, what is the medium of your reaction? Like
in assembly, talking about assembly,
yes.
It's in DCM.
It is in this. It's not in water.
It's a microarray, right?
Yes, but only.
This assemblies happen in solution.
Yes.
And then the solution we can broadcasting and investigate.
No, because you said your main interaction is dipole-dipole, right? Your main interaction in the assembly. So, I was wondering if you change the medium.
That is, we have little limitation. That is making a core as AU25 itself is a very fast work for us. And then based on the AU25 polarity, it's like a BZM only. So if you try to change the polarity of solvents, either cluster will decompose or it may not be stable.
And it can decompose and it can get different structures.
Yeah, that is also possible. But like that, as I told, like we have only limited resources, limited students.
Yeah, I understand that can be.
Yeah, that is also a possibility.
You mentioned the need to avoid the fake notes. What about the durability of fake?
We tested for a year. Still, like throughout that year, we were able to read this QR code.
Is it reactive to acid?
No, and then the currency will not be stable, even in the acid. We have to find out a situation where like we are using the currency. That condition we satisfy. And then one more thing, basically this cluster we can only make it. Okay, it is not available at the present in Shibu. That means these optical properties are unclonable. Nobody unclone the optical properties of nanoclusters. That very few people can decode. Okay.